Well, last time we saw that the solutions of the equation minus p-Laplacian equal to 1 have strange limits when p goes to 1 and when p goes to infinity. And we have calculated them for the case of a ball. And today I want to show you at least what happens when p goes to infinity for a general domain. So we study the behavior of up, solution of minus p-Laplacian u equal to 1 in omega u equal to 0 on the boundary as p goes to infinity for general omega. And the first thing that we do is we have to realize that the functions up are uniformly bounded. Get uniform bounds. On this family of functions, p greater than 1. Because when we have uniform bounds, then we have compactness and we can pass to the limit and so on. So I said these viscosity solutions are unique and weak solutions are unique. So the weak solutions that we get are the unique viscosity solutions. And since up is not only a viscosity solution but also a weak solution of this equation, we can use the formulation for weak solutions.
Bernd, I think that not for p greater than 1, because when p tends to 1, we can fail.
Yes, yeah. Actually, for p greater than n, I will get it. So up is a weak solution. That means that the gradient of up to the power p minus 2 gradient u gradient phi is equal to something. And if I take phi as a test function, I get that this integral is equal to integral up. So that's the L1. I can estimate this by the L1 norm of up, and the L1 norm I can estimate by the L2 norm. So by Hölder's inequality, this is up L2 norm. Oops, L2 norm. Okay. Now the L2 norm of up I can estimate by the L2 norm of the gradient of up. So this is 1 over the first directly eigenvalue of omega times gradient up in the L2 norm. And since this first eigenvalue is bounded below by the first eigenvalue for the corresponding ball of the same volume as omega,
Square root of lambda.
Square root of lambda. Okay, yes. That's right, yeah. I can bound this below by something omega to the 1/2 square root lambda 1 of omega star. That depends also on the modulus of omega times the gradient of up. Excuse me? Omega star is the ball of same volume as omega. And we have this Faber-Graan inequality that says the first eigenvalue of any domain is bigger than the first eigenvalue of the ball of same volume. Directly eigenvalue. So and now I try to estimate this by gradient up to the power p. Here I have gradient up to the power squared. So I get here a 2 over p, and then I get, if I did not miscalculate, the volume of omega 2 minus 1 minus 2 over p.
This is square of norm, so 1 over p.
No, here I had the integrand used to be gradient up to the power square. Yes.
Yeah, but
now I take p over 2.
Norm,
yes.
Yeah, but it is norm in the left-hand side, not integral. It's
Square of the norm. Ah, it is norm. Okay.
Yeah.
Okay. Here's 1 over p. Ah,
And here
1 over p.
1/2 minus 1p.
Minus 1 over p. Okay. Yes, that's right.
And 1/2.
1/2 minus 1p. Modulus of omega 1/2 minus 1p.
That's right. Okay. So anyway, here I have the p's power of this, and therefore it shows that this integral remains bounded. So what we know is that gradient up in the LP norm is bounded by some number m, which is less than infinity. And now we can also show, now we choose a number s bigger than n and less than p. We will send p to infinity and keep s fixed. And then we can find out that the gradient of u p in the S norm can be bounded by the gradient of up in the P norm times some power of omega. Again, I hope I calculated correctly. P minus S times S. And that goes to something which is also finite. So what we have shown is that this gradient of up that u is in W is in LS. And since there's a Poincaré inequality, we have also shown, because we have zero boundary conditions. So this shows that up are uniformly bounded in W1S0, and then by Sobolev embedding theorem also in some C1 alpha, as in C0 alpha for a suitable alpha. So they are equi-Hölder continuous, and then since the embedding of W1S into C0 alpha is compact, we know that after passing to a subsequence, up will converge to some function u infinity in C0 alpha, and in particular uniformly in omega. Okay. And then also u infinity will be a continuous function. So that is a good candidate for a viscosity solution to some limiting equation, because viscosity solutions should be lower semi-continuous on one hand, upper semi-continuous on the other hand, and here we have a continuous function that is a good candidate. That's the first step. Second step. Now we want to show that U infinity is viscosity solution for something. And so we show first that it is a viscosity subsolution. And to do that, we suppose that we have a smooth test function and that this test function touches our continuous function U infinity in some point x infinity in omega from above. Well, then also the following function v tilde v plus a large constant times x minus x infinity square. This touches at x infinity from above. Oops. So here I have a function u infinity. Here I have a function v that touches from above in some point x infinity. And the v is a genuine parabola, above a genuine parabola. Now the function up converges uniformly to u infinity, so up will be in some epsilon neighborhood here. And since v has a strict local minimum in the point x infinity, the function v minus u p will also have a minimum in the point xp, which is close to x infinity. V tilde minus up has a minimum close to x infinity in a point xp. And then I define v hat of x to be v tilde of x plus up in xp minus v tilde in xp. Then this function touches up from above only in xp. So this may be a little bit shifted. Here's the point xp. Okay. Now we know that up is a viscosity subsolution. And this means that if up is touched from above in a point xp, then a certain differential inequality holds for v. So we know that minus the gradient of v hat in xp to the power p minus 4 times gradient v hat in xp squared times Laplacian v hat in xp plus p minus 2 times the infinite Laplacian of v hat in xp, that this is less or equal to 1.
Why less or equal?
Excuse me?
Why less or equal?
Because it's a subsolution. Yeah, viscosity.
For V.
Yeah, UP is a subsolution, and therefore we have here this inequality sign. For super solutions, we have an opposite sign. Now, the gradient of V does not change in passing from V hat to V. It's the same gradient in the point.
What about parabola?
No, that's true. No, that's true. Yes. We shifted the parabola only down a little bit. Yeah. Okay. And now we pass with this. This is less or equal to 1. Yes. So now as xp tends to x infinity, we can pass to the limit here on the left-hand side. Because v is a C2 function, right? So the second derivatives depend continuously on the argument. And as xp tends to x infinity, we get that we may take limit on the left-hand side. And we distinguish some cases. If the gradient of v hat the gradient of v hat in xp tends to the gradient of v in x infinity. Yes. Because as p tends to infinity, first of all, the gradient of v hat is the same as the gradient of v tilde. And the gradient of v tilde in xp, when xp tends to x infinity, it tends to the gradient of v. Yes. And the second gradient of v hat in xp tends to the second gradient of v tilde in x infinity. You disagree?
Yeah, that's good.
No. Okay. So now we distinguish two cases. If the gradient of v in x infinity is bigger than 1 in modulus, then this term becomes bigger than 1 in modulus, and when we take it to a large power, it goes to plus infinity. Then the gradient of v hat in xp to the power p minus 2 is at p minus 4 goes to plus infinity. And therefore, this inequality can only remain true if this bracket here is greater or equal to 0, because we have a minus sign here. If this round bracket here is negative, then the left-hand side would go to plus infinity, but the left-hand side is bounded by 1. uniformly.
Can't it
Excuse me?
tend to zero?
What?
Can it tend to zero?
Yes, it could tend to zero fast enough, yes. So it has to be greater or equal to zero, yes. And this means that the infinity Laplacian of V tilde at xp is greater or equal to 1 over p minus 2 times the gradient V tilde at xp squared times the Laplacian of V tilde in xp as p goes to infinity. But this here is something that is bounded, and this is something that is bounded, and this is 1 over p minus 2, so this one goes to 0. And then we can conclude that minus the infinity Laplacian of V tilde in x infinity must be less or equal to 0. Now you can do that for any number m here. If you make the number m small and let it tend to 0, this still remains true. Send m to 0, then minus the infinity Laplacian of v in x infinity is less or equal to 0. So this is one possibility that can occur. The other possibility is that the gradient of v in x infinity is less or equal to 1. Then the gradient of v in x infinity minus 1 is less or equal to 0. So in any case, we find out that the maximum of dv in x infinity minus 1 and minus infinity Laplacian of v in x infinity is less or equal to 0. Or u infinity is a viscosity subsolution of the equation maximum of du minus 1 minus infinity Laplacian u less or equal to 0. So that was the second step. Third step. You take a u infinity and take a test function w that touches from below. if W is smooth and touches U infinity from below, in X infinity, then more or less a modification of the function W touches UP W hat touches UP from below in the point XP. And then we use the reverse inequality here. And since UP is a viscosity supersolution, we have that minus the gradient of W in XP, W hat in XP to the power P minus 4, and here same expression with W, gradient W hat in XP squared times Laplacian W in XP plus P minus 2 infinity Laplacian of W hat in XP. This is greater or equal to 1. Now, if the gradient of W hat of W in X infinity is strictly less than 1, then this term goes to 0. And then we have 0 greater or equal to 1. Then the left-hand side goes to 0. And that is a contradiction. So this cannot happen. Therefore, the gradient of W in X infinity is greater or equal to 1, or this minus 1 is greater or equal to 0. And this round bracket here is less or equal to 0. And as P goes to infinity, this means that minus the infinity Laplacian of W in X infinity is greater or equal to 0. So they are both greater or equal to 0, and therefore the minimum of dW in X0, X infinity minus 1 and minus the infinity Laplacian of W in X infinity is greater or equal to 0. And U infinity is a viscosity supersolution of minimum of these two expressions, the U minus 1 infinity minus infinity Laplacian of u greater or equal to 0.
Very short question. What
Excuse
was
me?
the reason to add this parabola?
Excuse me?
What was the reason to add the parabola?
If you have, I wanted to make sure that the points xp are close to x infinity.
Okay.
Yes? Because, I mean, suppose you have u infinity like this, and here's the point x infinity. And you have a function v that touches u from above.
Okay.
On a large set. Well, the function, this is u infinity, this is v, yes? The function v, the function up could, you know, be like this, yes? So I wanted them to be close together. But this is sort of a standard trick that one says, okay, it is enough to actually study this for functions v that are sufficiently steep, whose second derivatives are sufficiently large. So we have two inequalities, this one and that one. And I must confess, I do not see how to draw from this the conclusion that actually the first one is always satisfied, because this is what is claimed. There's a paper of Bhattacharya. So there's the theorem. Bhattacharya. Di Benedetto and Manfredi, that says u infinity is a viscosity solution of du less or equal to 1. But at least we have shown a big step in that direction. The proof that they give goes over pages and pages, and I must confess I could not follow the proof, so I tried to make up my own proof, and I got only this far. If one of you sees how to draw the final conclusion, I'll be happy to learn. In any case, the limit of this problem is that problem, and this is something that one would not expect. The iconal equation. So u infinity is not a solution of minus the infinity Laplacian u equal to 1. In omega u equal to 0 on the boundary. But you can calculate, this equation is of independent interest. If omega is a ball, a solution of minus infinity Laplacian u equal to 1 is u of r what is it, r to the 4/3 minus little r to the 4/3, up to a constant. And this function is of class C1 1/3. Because when we get close to the origin, this tells us the exponent. It's not a classical solution. Incidentally, the infinity harmonic function x to the 4/3 minus y to the 4/3 also had this class of regularity. And it is an open problem whether actually solutions of this equation with a nice and smooth right-hand side, 0 or 1 or C infinity, always have this kind of regularity. It was a major result to show that in 2 dimensions, solutions are of class C1. But C1 1/3, people have not been able to prove. And in higher dimensions, people don't know how to prove it. So the next remark that I want to make is, how can we understand the behavior of UP as p tends to 1? How can we understand the behavior of UP as p tends to 1 for a general omega? Now, remember UP minimizes E sub p of u. That's 1 over p, gradient of u to the power p minus u dx. And formally, E sub 1 of u is the integral of gradient u minus u. dx. And we already know that u will be positive because if it minimizes this integral, then replacing u by the modulus of u will make this smaller, so u will be non-negative. And this integral of u, we can think of it as a bunch of horizontal layers that are integrated with respect to height. So we measure the height from 0 to the maximum of u of level sets of u. So this is the set on which x is greater than t, and we take that measure and integrate it over dt. Then we have represented this integral. This is called Cavalieri's principle. In high school, I think one learns this. And this one here can be expressed by the co-area formula. So this is nothing but the boundary of the set x greater than t. And that has n minus 1 dimensional measure, and we integrate that one. Okay. Now when we look for a minimizer of this integral, we try to make, well, the integrand as small as possible. Suppose we manage to get the integrand smaller than 0. Then it will be good to send the maximum of u to plus infinity. This happens for a large domain, when omega is a large domain. So let D be a subset of omega. Try to minimize the boundary of D, length of the boundary of D minus the volume of D, or the ratio minus 1. And let's do this, say, for a square. If D is a small set, then the square may have more than one component. Then we can replace it by a disk D star that leaves this invariant and makes this smaller. So this is what the optimal D will look like. And in fact, for such a D star, we have 2 pi times the radius over pi times radius squared. That is 2 over rho. Is this ratio? Yes. 2 over rho minus 1 becomes negative if rho is bigger than 2. Yes. So when rho is bigger than 2, then the ball D star has a radius bigger than 2. Well, suppose this is an interval from -1 to 1. Then a small set does not have this property, so this radius will always be less than 2, and the integrand will be positive, and it will be good for the solution to have its maximum at 0, because the integrand is positive. Yes. So what we expect is for small omega that the integrand is positive, and then UP will tend to 0. For large omega, we expect that the integrand is negative, and that means that UP will go to plus infinity, because to make this minimal, we have a negative integrand, then it will be good to have the maximum of u very large. And there's an in-between situation. Where the integrand can be made equal to 0. So consider the minimum of this volume, the perimeter of D over the volume of D among all sets D that are contained in omega. And that's a geometric variational problem. So given a volume constraint, you try to minimize perimeter, you get something that has constant mean curvature. In 2 dimensions, it has constant curvature. So it is a domain that is bounded by circular arcs. Whoop. Or it could be a domain like this, but then when you rescale it so that it touches the boundary, you find out the domain that minimizes this expression for a square is a rounded square. And that's just one-dimensional calculus to figure that out. And we call that the Giga set connected with omega. Well, this is called the Giga constant. And omega c is Giga set. Now, if the Giga constant happens to be equal to 1, then this is equal to that. The integrand is 0. Yes. If the Giga constant. No. We consider this. Okay. If this if the perimeter minus the volume of omega c is less or equal to 0, even, well, if it is equal to 0, then the function u of x, characteristic function of the set omega c, is a minimizer of E sub 1.
Or arbitrary multiplier.
Yeah, with an arbitrary multiplier, any constant, any positive constant. Yes. So this explains why we have discontinuous solutions somehow in general. And when you plot these functions for larger squares, they tend to converge to the characteristic function of this Giga set. And actually, if omega is a ball, then the Giga constant is n over r. 2 over rho we had here in 2 dimensions. And then the boundary of a ball of radius r minus br, this is n over r minus 1 times the volume of br. And this tells us why there is different behavior when r is bigger than n or when r is smaller than n of the solution, of the radial solution. Okay. So we have looked at solutions of the Dirichlet problem where there was constant right-hand side in the equation and 0 boundary conditions. Instead of minus p-Laplacian u equal to 1, u equal to 0, one can also study minus the p-Laplacian equal to 0 and u equal to a given function g on the boundary in omega, and see what happens. And then if we call the solutions to these problems up, they converge to a viscosity solution of minus the infinity Laplacian of u equal to 0 in omega u equal to g on the boundary as p goes to infinity. And this boundary value problem has a unique solution. In the viscosity sense. Yes.
The previous problem, the solution of previous problem converges to something different.
Yes, yeah.
And how does it the behavior change? Is it no?
Well, one does the same thing that I did. You touch from functions with test functions from above and from below, and in the case of non-homogeneous right-hand side, somehow the right-hand side was giving you a different information than when you have zero. You do the same thing. You take a test function for up from above. So you get minus gradient v to the p minus 2, and then Laplacian v times gradient v squared plus p minus 2 infinity Laplacian v. This should be less or equal to 0 for any smooth test function that touches from above in a point xp. And then you send p to infinity. So you put this term on the right-hand side, you divide by p minus 2. In the end, you have here minus infinity Laplacian of v is less or equal 1 over p minus 2 times... So, since this is less or equal to 0, here we have gradient v squared Laplacian v. Now this is a smooth function, and the argument xp approaches x infinity, so this remains bounded. This one goes to 0, and this one is here.
So we can take, for example, the problem with some constant in the right hand side,
yes,
which changes with p, and then
this one can also do, yes, yeah. But already the constant independent of p is challenging enough, yeah.
Yeah, but
yeah.
In this case we see that there is a different
Well, you can also take a right-hand side that changes with p that looks like this, and then pass to the limit. In the eigenvalue problem, then you get, oops, then you get still a different limit, yes. That has been done. Now what happens for p equal to 1? When p goes to 1, we do not have sufficiently good bounds on the functions up. Maybe we get bounds in bv or something, yes, but that's not enough to have uniform convergence and to show something that some limit equation holds. When p goes to 1, formally the Euler equation is minus the gradient of u to the power p minus 2. Well, here we had a p minus 1 times the second normal derivative plus n minus 1 times h times the first normal derivative equal to 0. So when p goes to 1, this term becomes 0, and this one is 1 over the modulus of gradient u. No, this is 1 over modulus of gradient. Yeah, 1 over modulus of gradient u. Okay. And du by du is negative, the exterior normal derivative. So minus du by du is equal to the modulus of gradient u. So what we get is n minus 1 times h equal to 0. And in 2 dimensions, the mean curvature is the curvature. This means that the curvature of each level Z, each level curve, is 0. So level curves must be straight lines. Now here's an example of such a problem. Suppose D is the unit disk in R2, and the function G, which is a function of the angle on the unit circle, is just the cosine of 2 times phi. So the angle phi is measured from here. When phi is equal to 0, the cosine is 1. When phi is equal to p, the cosine is 1 again. When it is pi over 2, the cosine of 2 phi is minus 1. And here also minus 1. What?
It's trivial.
What is trivial? There are many solutions. So now I take a function, I pick a point here, yes, where the g is equal to lambda. And here I take horizontal level lines, and here I take vertical level lines. And here I set u identical to lambda. I get a whole family of solutions. So, and this family can be parameterized. So let me see. So u lambda of x and y can be given as 2x squared minus 1 on the left and right of the rectangle. It is lambda in the rectangle, and it is 1 minus 2y squared on top and bottom. And the graph looks like this. So it is just a flat, no, it is a paraboloid going this way and that way. One can show each u lambda is a viscosity solution of the limit equation. So the limit equation has many viscosity solutions, but only one minimizes E sub 1 of u. Now E sub 1 of u contains modulus of gradient u. So it is the total variation of u. And sort of the rationale why this is the case is if you measure the length of this line and that line, it is longer than the length of this line and that line when you have a right angle here. So so the total variation of this function is bigger than the one when lambda is equal to 0. Only u0 where you have the square here as a rectangle. This gives you the one that has minimal total variation. Total variation measures the length of level lines. And sort of by symmetrizing, the length of level lines becomes shorter. So in the first part of the lecture I made a mistake, and let me correct the mistake. In looking at subsolutions, I distinguish two cases. In the first case I got this inequality, in the second case I got that inequality. Since one of the two cases is always true, the minimum of these two functions is less or equal to 0. I had written maximum, minimum. And so u infinity is a subsolution of this, and we had seen it is also a super solution, and therefore u infinity is a viscosity subsolution of this equation. And as I said, I cannot reconstruct how the how Di Benedetto and so on arrived at their Hamilton-Jacobi equation, at the iconal equation. Anyway, we have looked a little bit at what happens when p goes to 1. And there the total variation of functions plays a role. Total variation plays a role in a totally different context in mathematical image processing. In mathematical image processing, you have a blurred image, a disturbed image of some object, and you want to make the image a little bit sharper. One can think of a black and white image as a function that takes values on a grayscale between 0 and 1. Say 0 is white, 1 is black, and anything in between is a gray value. And of course, if you have, I don't know, an object that has originally, say, this kind of grayscale, after transmitting some photo signal or so, this may be disturbed a little bit. And then you would like to reconstruct the original image. Now you can do this by, you can approximate any function in L2 by step functions, for instance. But step functions have a lot of steps, and in higher dimensions this means that you get many contours. And you want to limit the number of contours. You want to have as few contours as possible, and this means you want a small total variation of the image. So you take the blurred image, take the disturbed image u0 as an initial value for some evolution process. Equation. For instance, for so-called TV flow, total variation flow, and there the equation is u sub t minus divergence gradient u over modulus gradient u equal to 0. And then you see what happens, how the function u develops in time. And let us see what happens. We make an Ansatz. U of t and x is some function capital T of t times a function, what do I have? V of x, I guess. W of x. And then we get t dot times w minus the divergence of gradient w over modulus gradient w equal to 0.
T.
T. Yes.
Excuse me.
The T cancels, yes? The T cancels. Now this is only x dependent, and we can separate variables. And you find out that minus divergence, well, t dot is the only thing that seems to depend on t. Everything else does not depend on t, so t dot cannot depend on t. T dot must be a constant. And minus divergence gradient w over modulus gradient w is equal to lambda times w. And when t dot is constant, that means that t is linearly decreasing. So the behavior of t over t looks like this. And this means after a short time everything has disappeared. Now, what happens with the function w of x? Well, w should be what some people call an eigenfunction of this operator. And I don't like the name eigenfunction, yes? But let's look at this equation. We know what the one Laplacian is. The one Laplacian is n minus 1 times h, right? So in 2 dimensions, it's minus 1 over r, what we have on the right-hand side. So if, say, w is the characteristic function of a ball of radius r, then all the level sets of w have curvature 1 over r. Then we have here minus 1 over r is equal to lambda. Or plus 1 over r. Minus 1 over, plus 1 over r, and minus 1 over r. 1 over r is lambda times w, yes.
Yes, but how can it be? It's 1 r
Only on the boundary, yes.
on the boundary.
That's the curvature of the level set, yes. If we have a general profile, say a function w, what this tells us is that the speed by which the function goes down to 0 is proportional to the curvature of a level set. And this means That's if I have, for instance, some small and highly curved dark objects. They disappear to zero very fast and the other ones remain. And therefore the total variation of the image decreases. And small noise goes away. I mean, noise that lives on a small scale. But I don't like this equation. So, because this is not an eigenvalue equation, an eigenfunction, if you have an eigenfunction, the left-hand side and the right-hand side should have equal homogeneity. And so I made a different ansatz. So, philosophy. Suppose u sub t minus some operator a times u is equal to 0, and a is homogeneous of degree d. Then separation of variables. Gives me a different behavior of the function capital T. T of t is equal to, well, if d is between 0 and 1, it gives me a t to the 1 minus d at 0 minus 1 minus d times lambda t, and this to the power 1 over 1 minus d. And for d equal to 0, this is this case, then it decays to 0 linearly. In any case, it decays to 0 in finite time. It grows like t of 0 times e to the minus lambda t if d is equal to 1 and there is polynomial decay if d is greater than 1. So the case d equal to 1 is the closest to the heat equation, and therefore I prefer the case of a one homogeneous operator. Now, the p-Laplace operator and the one Laplace operator, they are not one homogeneous. But is there a one homogeneous version? So I look for a one homogeneous version, one homogeneous variant of the p-Laplacian. And here is one. Now remember, the p-Laplacian is divergence gradient u to the p minus 2 gradient u. And if I multiply this with gradient u to the 2 minus p, then it is one homogeneous. And if I multiply it with 1 over p and a minus 1, it is also one homogeneous. And I call this the normalized p-Laplacian operator. This is homogeneous of degree 1. Of degree 1. That is minus the p-Laplacian of 2 times u is 2 times is minus 2 times the normalized p-Laplacian of u, or any other constant.
And what for is the constant divided by p?
In a minute. Yes. Now, in intrinsic coordinates, it turns out that the normalized p-Laplacian can be written as a convex combination of the normalized infinity Laplacian and the normalized 1 Laplacian. So that is p minus 1 over p times the normalized infinity Laplacian minus 1 over p. Well, let me leave out the minus sign. Times the normalized 1 Laplacian. And when p goes to infinity, it becomes the normalized infinity Laplacian. When p goes to 1, it becomes the normalized 1 Laplacian. Yes? Now let's see. And now when you look at the equation, u minus the normalized p-Laplacian equal to 0, you get solutions that have the property that decay like e to the minus lambda t, where lambda are eigenvalues of this operator. Let's look at some special cases. Let's look at the case p equal to 2. Then we have u sub t minus 1/2 times the Laplacian of u. That's the heat equation the way physicists like to write it. That's a factor 1/2 here, or I don't know. Case p equal to 1, u sub t minus, here we have the gradient to the power 2 minus p, gradient u, times divergence, gradient u over modulus gradient u equal to 0. This is an equation which shows up in the level set formulation of mean curvature flow. And there has been a series of paper by Evans and Sprague. I don't know, maybe in the 1990s. What do I mean by that? Suppose I have a block of ice, and heat is coming from outside. Here the heat is attacking from many different directions on a small area. Therefore here it will melt relatively fast. Here the heat is not so effective, so there it will melt slowly. So the speed at which this front moves inward is proportional to curvature. That's mean curvature flow, in proportional to mean curvature. And one way to describe this is to take this set as a level set of a function. You can take, for instance, suppose the set omega 0 is the set on which u0 is equal to 0, and u0 is the signed distance function of x to omega 0. It is plus the distance function here minus the distance function there. And then you take this function as an initial datum for this equation, and you look for the solution of this equation. And then you look at a later time, the function u of t, where does it have its 0 level set? Then this is where the domain omega 0 has gone. That's the level set formulation of mean curvature flow. And of course, this is a nasty equation. We don't know what it means when gradient of u is equal to 0 here, because here we have 0 by 0. And what Evans and Sprague did was they replaced gradient of u by the square root of epsilon squared plus gradient u squared. Then you have here a denominator which is non-zero, and here everything becomes nice, and then you send epsilon to 0. And this is sort of a viscosity limit. So that's a special case of this equation. Another special case is u sub t minus the normalized infinity Laplacian, and that is just the second derivative of u normal to a leveled surface equal to 0. And that's an equation that Utin and I studied. And for p in between, you have in between solutions. Now, let's recall again. So this one Laplacian, this normalized infinity Laplacian is a pure second derivative normal to a leveled set of u. This normalized one Laplacian are second derivatives tangential to leveled sets of u. So here we have a convex combination of one second derivative and the orthogonal other second derivatives. And since for p between 1 and infinity these two coefficients are both positive, we have a truly elliptic operator here. So this, in some sense, this is a more benign elliptic operator than the p-Laplacian operator. It is not so degenerate, yes. And so it makes sense to look at this equation. And you can prove, for instance, if u solves star, then d by dt of integral gradient u to the p decreases in time, is less or equal to 0. So in particular, when p is equal to 1, the total variation decreases. And I had a PhD student who was also good at programming, and she took some initial datum for this equation under Neumann boundary conditions, no flux conditions on the boundary, and she calculated the solution for different values of p. And I would like to show you the results. Maybe we have to pass this around. What we see here on the left is a photo of the Cologne Cathedral. And on the right, so-called pepper and salt noise has been added to the photo. That means some pixels have been replaced stochastically by black or white without paying attention to the gray value. And in fact, 50% of the picture has been destroyed this way. 50% pepper and salt has been added. And now the question is, let's take this image as an initial datum for this equation, for different values of p, and see how it develops. Now, after 5 identical time steps, for a p that is close to 1, it looks like this, and for a p that is large, close to infinity, p equal to 10, it behaves like that. So the pictures are different, yes. The same initial datum, the same time steps, the same numerical method. And then when we go a little further, after 15 identical time steps, p equal to 1 is much more blurred than large p. So this is a numerical experiment that was that was somewhat surprising. Let me return. So this is the original picture, and this is the one with pepper and noise added. And then I take the disturbed image and the same perturbed image for both equations, one for p equal 1.2 and one for p equal to 10, after 5 time steps, after 15 time steps.
I saw some different variants of image
processing equation.
This type by nonlinear parabolic.
Yes, there are many such equations. In fact, this is a field of mathematics that is somehow in the state of alchemy. That whoever invents a method says this method works nicely for a particular problem, and my method is the best somehow. And these are recipes somehow. One of the first and very successful recipes was given by Perona and Malik. So, two electrical engineers, I think, Perona and Malik. They took an equation u sub t minus divergence, and here they had a function a gradient u equal to 0. And the coefficient a behaved a little bit like this. So a of t was, I don't know, 1 over 1 plus t squared, I think. Yes. And the philosophy was, suppose...
If the gradient is large, then you don't change it.
When the gradient is large, then we have small diffusion, then we don't change it. So when we have a sharp edge somewhere, the gradient is large. And if we have small perturbations, then these get smoothened out. And this works fantastic, yes? Very nice. But there is no nice theory, because for this equation you find out if you write it in these intrinsic coordinates, you take the divergence, yes? So you have a Laplacian here, and then you have a derivative of a. And you get some coefficient b times gradient u times the second derivative in normal directions plus a times the second derivative in tangential derivative, minus a times the second derivative in tangential directions. Something like this. So this is the same a. And this one, this b, is a composition of a and a derivative of a. And since a prime is negative, this changes sign. So the behavior of b is somehow like this, the qualitative behavior. And when b is negative, let's forget about this term. When b is negative, you have u time derivative plus a space derivative. And that's a backward heat equation. utt plus uxx is a backward heat equation. Now, backward heat equations have the property that they take something like the Gaussian distribution and convert it to the delta distribution. And therefore, people have said it's hopeless to prove maximum principles or something like that for this kind of equation. But in fact, I was able to prove a maximum principle. The L infinity norm does not increase for such an equation. This is a paper with Kutev in early 90s, yes?
And the reason is that basically this backward equation doesn't go backward a lot.
No, it does not go backward a lot. Yes, okay. So let me show this algorithm. Whoop. Let me see, do I have it here? No, I don't have the movie here. Okay. So if I apply such kind of algorithm to this picture, the number of contours decreases, and you get more or less an impressionistic image of the Cologne Cathedral.
So this is black and white.
No, this is the edge detector that tells us where there are sharp differences in height. And here, for instance, you see the cloud has many different grayscales. Over here, the cloud has only 2 or 3 different shades of gray. A light gray and a medium gray and a dark gray. Okay. So there are many theorems that still need to be proven, and then it's very important that one goes into this kind of research. For instance, images where these diffusion filters are used in medicine. You have an ultrasound picture of some organ. You want to know where exactly is the cancer. How much can I rely on this picture? And okay, these machines tell the doctors, okay, this is the sharp edge, cut there. But we have no idea how reliable this is, yes. Of course, there are also other conceivable applications in military reconnaissance. You want to see where are the bunkers or something, yes. What kind of submarine do I see on the radar screen? Is it our own or is it somebody else's? And things like that. Anyway. Now, since this operator has recently been rediscovered in a different context, it shows up in some stochastic game. And I don't know how to explain the game to you, so it's also called the game-theoretic version of the p-Laplacian operator. The game-theoretic version of the infinite Laplacian operator shows up when one models a game called tug of war. Tug of war means that you have 2 teams of people that pull on a rope in opposite directions, and this is called tug of war. And if one tries to model this, one comes up with something called a value function, and the value function satisfies the equation infinity harmonic equal to 0. And then there is tug of war with noise, then you come to the p-Laplacian. So it is interesting in itself to study this operator. And to look, for instance, for this equation and see what happens. In a ball of radius r with 0 boundary conditions. And when you calculate the solution, you find out up of r is equal to p over p plus n minus 2 times r squared over 2 minus r squared over 2. And for n equal to 2, it is independent of p. So, for different p's, the equation has the same solution. Another thing that you can do is you can try to study eigenfunctions of this equation. And it turns out, well, the equation was again, what was it? P minus 1 over p, u, in polar coordinates, u double r, plus n minus 1 over p times r, u sub r equal to 0. Equal to plus lambda times u equal to 0.
It's for radial.
Excuse me?
It's for radial.
For radial eigenfunctions.
But surely all eigenfunctions.
No. We don't know if all there may be non-radial eigenfunctions. Yes. But let's at least look for radial eigenfunctions. Well, this looks a little bit like the Bessel equation, except that you have a p minus 1 over p here. So you bring that constant over here, and then it is a Bessel equation. It's the Laplacian equation in some space of fractional dimension. The number n minus 1 here is replaced by n minus 1 over p minus 1. And then in this space of fractional dimension, you can look for solutions of the Bessel equation. You get a series of Bessel functions, and they are also normal in a suitably weighted space. I mean, normally we have r to the n minus 1 dr as a weight, but now it is something that depends also on p. Yes, and we get a complete class of radial eigenfunctions. Non-radial eigenfunctions, I don't know. In fact, I don't even know if the first eigenfunction is radial or not. On a ball.
For elliptic equation.
Well,
Can't you do this centralization?
no, you cannot, because this operator is not variational. It is not variational, yes? And that causes a lot of problems. It is not variational. So you cannot say it's the minimizer of some functional. So it satisfies p-Laplacian lambda times u gradient u to the p minus 2. So that's the equation, yes. And now this is not the Euler equation of a nice functional. It's not variational. Well, times p. So. Yeah. Of course, one can also look for now. Since you mentioned variational methods, one can define eigenvalues for the p-Laplacian. As minimizers of this Rayleigh functional. Yes. For p equal 2, it's the usual Rayleigh functional. And then what you find out is that the corresponding Euler equation is minus the p-Laplacian equals lambda times u to the p minus 2 times u. And there it is known that the first eigenvalue on a ball, the first eigenfunction on a ball is radial. The first eigenfunction is positive, and it is unique modulo scaling. And to show that it is a simple eigenvalue is not so simple. There is a convexity argument behind it.
I think they should know.
So you presented this.
I thought this idea.
Okay. But let's look for the second eigenfunction. The second eigenfunction, when p is equal to 2, the second eigenfunction on a square can have such a nodal line, or it can have a diagonal nodal line. Plus, minus. Now, for general p, one of these is preferred. One knows that for p equal to infinity, one gets this, and for p equal to 1, one gets this. Conjecture that this is also true for p between 1 and 2, and that one is true for p between 2 and infinity. So numerical experiments suggest that this should be the case and that should be the case. Numerical experiments also suggest that the level line on a disk, for the zero line on the disk for the second eigenfunction should be the diameter of a disk. But I don't know how to prove it.
As I know, not Radek and somebody else, that the second eigenfunction is not radial, at least.
Yes, yeah. It's not radial, and also one can show that it does not have. Well, no, it's not radial. Yeah, that's right.
Yes,
Yeah.
But it was
Yeah.
very tough.
Yeah. And one can ask similar questions for the Neumann problem. So here in this problem, one can also discuss p to 1, p to infinity, and then one can minimize this on w1 p0. Then we have u equal to 0. Or one can minimize this on the set of functions. W1p minus 0 intersect with functions that have this mean value equal to 0. And then you get the same equation, but now with Neumann boundary conditions. Let me call this nu here, Neumann value, eigenvalue, or mu. Nu is. So the first eigenvalue for this equation is 0, the first eigenfunction is constant, and one looks for the first non-constant eigenfunction. And that's a function that changes sign. So it must be positive somewhere, it must be negative somewhere. On a general domain, it will be positive somewhere, negative somewhere. This can never happen. That's difficult to show, even for 2 dimensions, even for p equal to 2. But for general p, one has to think of different proofs.
And why can't it happen?
This one? Well, for p equal to 2, for p equal to 2, one would know that the second Neumann eigenvalue of omega is equal to a first Dirichlet eigenvalue of omega plus, because u has only one sign on a smaller domain here, yes? And the second eigenvalue of a smaller domain, Dirichlet eigenvalue, is bounded from above by the second bounded from below. By the second eigenvalue of a larger domain, because I have more functions, and that one is bounded from below by lambda 1 of omega sharp. And by some inequality of Kornhauser and Steckold, this one is bounded from above by mu2 of a ball. But these eigenvalues are known to be explicitly known. They are zeros of some Bessel functions. And unfortunately, they do not satisfy this inequality, this chain of inequalities. They satisfy the opposite one. So that's a contradiction. In for general p. What?
So basically, you do what? Okay.
No, you assume that there is a closed nodal set inside omega.
Yes.
Then this leads to a contradiction, and therefore there cannot be a closed nodal set. Therefore, the nodal line must touch the boundary somewhere. Yes.
And if it touches, it must be transversal to it.
Yes. Yes. Well, this needs more arguments, but then it touches transversally. Yes.
Okay.
I mean, in the book of Korn and Hilbert, for instance, you find a theorem that if two nodal lines of the Laplacian cross, then they cross under a right angle. If 3 of them cross on a point, they cross under 60-degree angle, and so on. Yes, and one can. That's a nice exercise, I think, in spherical harmonics. Yeah. Okay, I think my time is up. I have only touched a few points. If you want to read more about it, look on my webpage. I have some papers, and in these papers, also survey papers. In these papers, I give a lot of references. And if you want copies of these papers, I'm happy to send electronic versions of the papers to you, because I know sometimes they are hard to get. Thank you.